We've just looked at indicators and we all know what indicators are used for. Yes, that's right. Titration's the one amazing thing that unfortunately many people don't like. But that's the practical aspect of it. Let's look at titration on paper or on the screen. Say we have 50 centimeter cube of 0.1 molar HCl inside a conical flask. Let us titrate this with 0.1 molar sodium hydroxide. Yes, I know the amount of base required to neutralize the acid is 50 centimeter cube, but that's not what we're concerned with. Let's look in detail how exactly the pH of the solution in the conical flask changes as we add more base. So there are a few volumes of interest that we want to look at, and here they are. At the start of titration, there is no added base. So we can simply find the pH at this point by taking negative log 10 of 0.1 molar, giving us a pH of 1. What happens when I add 20 centimeter cube of base? Take the initial number of moles of hydronium minus the number of moles of hydroxide, because they react, and this is the new number of moles of hydronium. Find a new volume because I added a solution to the original 50 centimeter cube, and then find the concentration of hydronium, then find pH. What happens when I add 40 centimeter cube of base? Do the exact same thing, and do the same for 49 centimeter cube as well. What about 50 centimeter cube though? All the acid would have been neutralized. We call this point the equivalence point. And since sodium chloride is a salt of a strong acid and base, and sodium is not highly polarizing, the solution remains at a neutral pH of 7. Finally, for the post-equivalence point, do the same for 51 centimeter cube. Now it will be calculating the amount of hydroxide ions instead. Take the number of moles of hydroxide minus the moles of hydronium initially, and you should get 1 times 10 to the power of negative 5 mole. Divide that by the new volume of 101 centimeter cube, in the right units of course, to get the concentration of hydroxide. Take negative log 10 to get the POH, and then take 14 minus that to get your pH. If you don't get any of the reasons for these calculations, you can watch the earlier videos. So if you took all these points, or rather if you took more points and plot a graph out of it, you get what is known as a titration curve, because it reflects the pH change during titration as you add more of the titrant into the conical flask. Notice how the pH change is really gradual, but near the equivalence point, there is a sharp increase in the pH. And this is useful because when we observe the sharp pH change, we will know that we have reached the equivalence point. And what would we better use but indicators to tell us that we have reached that point? But not just any indicator, the indicator needs to have a pH range that is within the change of the equivalence pH point. So if we look at the graph, we will need something that changes pH something between 4 and 10. A suitable indicator, bringing it back to the table from the previous checkpoint, will be phenolphthalein, because the indicator endpoint, or the point at which it changes color, lies well in the middle of the change of the equivalence pH point. That means when the equivalence point is reached, we would also have reached the indicator endpoint, and subsequently color change with further addition of the titrant will only prove that point. Aha.